Hey guys, today's lesson is about yield and we'll be mostly focusing on how to calculate percent yield, which is the amount of a reactant that was produced compared to how much you expected would be produced. So like I said, this lesson is about yield. We'll be talking about the difference between theoretical and actual yield and the reasons why they might not be the same as one another. Then we're going to calculate both theoretical and percent yield, as well as explain what that means. And then we'll briefly look at how to work backwards through percent yield to calculate the actual yield, which is something you're normally given. So the theoretical yield is the amount of a product, usually in grams, that you would expect to find at the end of your reaction once the limiting reagent has been all used up. If you aren't told in the question which reagent is limiting, you will have to calculate that first using the stuff we talked about earlier, like the last lesson or two. But once you have the limiting reagent, then you will just use the mole ratio to figure out the amount of product. And then the moles of product gets converted into mass using moles equals mass over molar mass. That is the theoretical yield. So really, we've already calculated theoretical yield when we were talking about finding the amount of product in the limiting reagent video. But now you just know it's called your theoretical yield. So that's all it is. It's just the exact same as what we did like 2 lessons ago. So we'll come back to these. The actual yield is usually given to you in the equation. It's the amount of product that is actually obtained at the end of the reaction. So you can't calculate actual yield just based on the mole ratio. It has to be given to you, or you can calculate if you're given the theoretical and the percent yield. There are a couple reasons why the actual yield tends to be lower than the theoretical yield. There could be impurities in the reactants, which increases the mass of the reactants, but doesn't produce any product. It could be that you just weren't as accurate as necessary with your measurements. It could be that you lost some of the product. Usually that happens if you have a gas as a product. That's really easy to lose. It just like escapes out into the atmosphere. Or it could be that you were like stirring or like transferring the product into like a weigh boat to measure its mass. And some of it just like stuck to the sides of the container or the stir rod or whatever. It could also be that the product is a precipitate and some of it dissolved. So as you know from your solubility table, precipitates are slightly soluble. So even though most of a precipitate is a solid, some of the precipitate can dissolve, and that won't be included in the weight of the product. You might also have a really slow reaction. And in that case, you might measure the mass of the product before the reaction is actually complete. And you might also have a reaction that never goes to completion and instead reaches a state of dynamic equilibrium where it's moving both in the forward and reverse direction at the same time and speed. And if that's the case, your reactants, neither of them are ever used up. And therefore you don't make as much product as you would have if the reaction had gone to completion and you had used up one of your reactants. So the percent yield is just the percentage of the expected or the theoretical product compared to how much was actually produced. We measure this as percent yield is the actual yield divided by the theoretical yield, and then of course multiply by 100 to turn it into a percentage. So for example, if I was expecting 100 grams, actually got 75, you would just do 75 divided by 100 is 0.75, and then multiply it by 100 to turn it into 75%. When you are determining your percent yield, first you calculate the theoretical yield, which we already talked about, and then you'll be given the actual yield, and then you just plug those both into the percent yield formula. The percent yield should always be expressed as a percent of mass, so both the theoretical and actual yield should be converted into grams before you plug them into your percent yield formula. You can also, like I said, sometimes be given the percent yield, and then you can calculate the theoretical yield and work backwards to find the actual yield. So let's work through some of these questions here. Again, if you want to go back and try some of these theoretical yield questions, you can if you want. But that's really just the first step of a percent yield question, and you will never be asked just for the theoretical yield unless it's a limiting reagent problem and you're asked how much product is being produced. But as far as like percent yield questions go, you'll never just be asked for the theoretical yield. You'll always be asked to kind of take the next step and find the percent yield. So we'll just go through these problems. We'll work through the first one together, and then you guys can try the next two on your own. Okay, so the first question says you have hydrogen, which is H2, reacting with carbon dioxide. It also tells you that you're making methane, which is CH4. And because that only accounts for my C's and H's, I must also have some oxygen left over as well. Our next step is to balance this, which we do by putting a 2 in front of the hydrogen, and then everything else is balanced. It says, what is the expected yield of the methane the expected yield of the reaction was 119.25 grams. The actual yield was 97.45. So for this one, we just have to do the percent yield is actual yield over theoretical yield. The actual yield, we're told, is 97.45. And it tells us the expected yield, which is the theoretical one, was 119.25. So all we have to do there is divide, which gives us 0.817, and then of course times by 100 gives us 81.7%. Okay, that was an easy one. So if you would like to watch me walk through the next one as well, you can do so. If not, pause it now and try it on your own. Okay, so the second number one here says we have chlorine gas reacting with an excess of potassium. Oops, sorry, I'm not showing you. So 24 grams of chlorine reacting with an excess of potassium in a synthesis reaction, which would make potassium chloride. It then tells us that 39 grams of the product is produced. It wants to know what the percent yield is. So because it tells us what the excess reagent is, we can just go right to dealing with our limiting reagent. I'm going to find the molar mass of both my limiting reagent and my product. So for chlorine, it'll be 35.45 times 2, or 70.9. For the potassium chloride, it will be 39 plus 35.45, which is 77.45. So that's my first step. My next step is to do moles equals mass over molar mass for my limiting reagent. So 24 divided by 70.9 is 0.3385 moles of chlorine gas. I'm then, as step 3, going to set up a mole ratio between my chlorine gas and my potassium chloride. And sorry, I just realized I hadn't balanced that yet. There we go. So that is going to be a 1-to-2 ratio. And if we cross multiply, we get 0.677 moles of potassium chloride. My next step, step 4, is going to be to use moles equals mass over molar mass to solve for the mass of potassium chloride. And you should get about 52.43 grams as the mass of potassium chloride. That is your theoretical yield. Anytime you have to use use the mole ratio to find the amount of something, that's always theoretical. So our last step then is just to find the percent yield by taking the actual yield, which is the 39 grams we were given, divide it by the 52.43 grams that we just solved, and you'll get 0.7438, which is 74.38%. Okay, now try the next one on your own if you followed along for this one. Okay, so the last question there has trinitrogen, dang it, I did dinitride instead of tetranitrile. Okay, changed your question. Tricarbon dinitrogen reacting with oxygen to make carbon dioxide. And then because we're making carbon dioxide, we must have nitrogen gas left over there. So I'm given the mass of the tricarbon dinitride and told that I have an excess of oxygen gas. I've also been given the actual yield of carbon dioxide. So I start by doing my moles equals mass over molar mass for my reagent and get 0.5938 moles of my limiting reagent. I set up a mole ratio between the limiting reagent and the product. It is a 1-to-3, so I'll get 1.78 moles. And then I'll plug the 1.78 moles and the molar mass of my product into moles equals mass over molar mass and solve for the theoretical yield, which is 78.4. Note, we do not use this grams of our product, which is the actual yield, until we get to the percent yield question. People sometimes get confused and think it should go somewhere in this formula. It doesn't, okay? So now that we have the theoretical yield in grams, we can take the actual yield of 42, divide it by the theoretical yield, multiply it by 100, and you'll get 53.6%. Okay, the very last thing that we're going to be doing is putting together the stuff that we learned in the limiting and excess reagent lesson with this percent yield stuff to calculate the percent yield in these first two questions, and in the last case, actually work backwards for the last part and calculate the actual yield. So yeah, once again, I'll walk through the first one with you guys if you would like to follow along for that, and then try the next two on your own. Okay, so for the first question, we have nitrogen gas reacting with lithium in a synthesis reaction, so that would make Li3N once we cross over our charges. And then I will need to put a 2 here and then a 6 here to make that balance. I was also told that I have 42 grams of nitrogen gas, 40 grams of lithium, and that I make 52 grams of my product. So the very first thing I have to do, when you're not told which one is the excess and which one is the limiting reagent, you must start by figuring that out. I'm also going to find the molar mass of both my product and my two reagents. So for nitrogen, it is going to be 28. Lithium is 6.94. And then it's 34.82 for lithium nitride. Then I'm going to do moles equals mass over molar mass for both of my reagents. I'll get 1.5 moles of nitrogen. That is the actual moles of that. I will get 5.76 moles of lithium. Again, that is the actual moles of that. My third step is then to set up a mole ratio between my two reagents, which is a 1 to 6. I'll plug in the amount of one, solve for the amount of the other. Doesn't matter which is which. And I get 9 moles of lithium needed. Now, as you can see, I need 9 moles of lithium. I only have 5.8-ish moles, which means that lithium is limiting. Now that I know that, I can go on to the next part, which is figuring out how much of my product is being produced. So finding the limiting reagent is kind of like the first part of this. The second part is figuring out the mass of my product produced, which again is the same thing that we did in the limiting reagent lesson. So I'll set up a mole ratio between my limiting reagent and my product, which is a 6:2 ratio. You could also do a 3:1 if you wanted. I'll plug in the actual amount of lithium that I have, which is 5.76 moles, and solve for the amount of lithium nitride. So I'll do 5.76 times 2 and then divided by 6. Again, you can do that in 2 separate steps if you want, but you should get that X is equal to 1.92 moles. Now that I know how many moles of lithium nitride I have, I can figure out how many grams I have by doing moles equals mass over molar mass of lithium nitride. I'll just multiply by the molar mass and get 66.85 grams. That is the theoretical mass of my lithium nitride. Now that I have that, my final step, and the only thing that we haven't done in a previous lesson, is to calculate our percent yield by taking the actual yield, which we were given in the question is 52 grams, dividing it by the 66.85 that we just calculated, which is 0.7779-ish, and then multiply it by 100 to get about 77.8%. Okay, try the next two on your own. Okay, for the second question, we have phosphoric acid, which is H3PO4, reacting with beryllium. We're making beryllium phosphate, which is Be3PO42, and hydrogen gas. We're given the mass of both our reactants as well as the beryllium phosphate. So I'm going to start by finding the molar mass of all of those and balancing my chemical equation. Then I have to identify which of my reagents is limiting. So I'm going to do moles equals mass over molar mass for each of them. you'll get 0.5306 moles of the phosphoric acid that you actually have, and 1.7 repeating moles of the beryllium that you actually have. Then you'll set up a mole ratio between your two reagents. It is a 2:3 ratio. Plug in an X for one of them and the actual moles of the other one. Find the moles needed of whichever one you didn't plug in. In this case, I found that I need 1.185 moles of my phosphoric acid. As you can see, I need way more than I have. I need over 1 moles. I only have about 0.5. Therefore, H3PO4 is limiting. Again, if you had solved for the amount of beryllium you needed, you would have had a smaller number than 1.7. So you would have needed less than you had, which would mean that the beryllium is in excess, and therefore the phosphoric acid is limiting. You then set up a mole ratio between your limiting reagent and the product. So it's a 2:1 ratio. I'll plug in the actual moles of the phosphoric acid, my limiting reagent, and cross multiply and divide to solve for my moles of beryllium phosphate, which is 0.2653. I then plug that into moles equals mass over molar mass to determine that I have 57.56 grams of the beryllium phosphate. That is the theoretical amount. And then my last step is to go to my percent yield. I take the 39 grams that I was given in the question divided by the theoretical yield that I just calculated, and then times it by 100, and you should get 67.8%. Okay, and for the third and final question, we have 35 grams of aluminum reacting with 1.3 liters of 5 molar sulfuric acid. It is making aluminum sulfate and hydrogen gas. We're told that the percent yield for the aluminum sulfate is 72%. We're asked what its actual yield is. So just like always, we're going to start by identifying our limiting reagent by doing moles equals mass over molar mass for the aluminum to get 1.314 moles of aluminum. And then for the sulfuric acid, we're not given grams, so we can't use moles equals mass over molar mass, but we can use C equals N over V to find moles, since we're given the concentration, the 5 molar, and our volume, 1.3 liters. So multiply by 1.3 and you'll get 6.5 moles of the sulfuric acid. Then we'll set up a mole ratio between our two reagents. It's a 2:3 ratio. Plug in an X for one of them and the actual moles for the other. If you did it the way I did, you'll get 4.3 repeating moles of aluminum needed. I need about 4 moles of aluminum. I have just over 1. Therefore, I need a lot more than I have, so aluminum is limiting. I then set up a mole ratio between my limiting reagent and my product, which is a 2:1 ratio. And I plugged in the wrong number here. Okay, let me fix that. Okay, sorry, fixed it. So set up a mole ratio between your limiting reagent and your product, which is a 2:1 ratio. We plug in the actual moles of our limiting reagent, cross multiply and divide, and you should get 0.6585 moles of our product. We then go to the moles equals mass over molar mass and solve for mass, and that gives us 224.65 grams of the aluminum sulfate theoretically. Then we go to our percent yield is actual yield divided by theoretical yield. I can plug in my percent yield as a decimal and then plug in my theoretical yield. I am looking for my actual yield. So I, of course, just multiply by my theoretical yield on both sides and get 161.75 grams as my actual yield. Now, some of you will want to be using this formula instead, just to remind yourself about the timesing by 100 thing. If you're using this formula where it actually has the times 100, when you plug in your percent yield, you'll plug it in as a number, not a decimal. And then your very first step will be to divide by 100, which will get you to the step that I just kind of started with here. Okay, but if you'd like to include that times by 100, you put your percent yield in as a full number. If you don't want to bother with the times 100 part, then you put your percent yield in as a decimal. That's the only difference. Okay, please let me know if you have any questions about this stuff. Good luck with it.